And let's start officially. So good morning, everyone. Welcome to a course which is delivered to you by LUMI AI Factory and MathWorks in collaboration. It's named Building Robust Industrial AI Solutions, Addressing Real-World Challenges with MATLAB and HPC. The event delivers an advanced overview of the design, development, and deployment of robust and scalable industrial AI solutions. You will gain in-depth insight into leveraging MATLAB in conjunction with high-performance computing infrastructure. For this, there will be hands-on exercises where you will be able to use Carolina, our supercomputer that we operate at IT for Innovation's National Supercomputing Center. And your tutor today is Akhil Gopinath, who is a senior AI academic liaison at MathWorks, working with global AI experts to advance innovative AI systems. And practical, I would like to ask you if you could rename yourself and use your full name and surname so that we can check the attendance list. Also, I would like to ask you to stay muted during the course. Also, because it's recorded, there will be time for questions when Akhil will give you space to ask. You can also ask your questions in the chat. We will be monitoring it, or you can speak up during the dedicated time. The question sessions and the hands-on sessions, as I said, will be cut out from the recording, and the recording will be available at IT4I's YouTube channel. Later on, we will send you an email when it's done. We do the post-processing of the recording, so it takes us roughly 14 days. And you can also get certificate of attendance after the course, but beware that we check the attendance and it's necessary to attend at least 80% of the course duration. And also we would then like to ask you to fill in the satisfaction survey, which we will announce at the end of the course. So this is from the practical point of view. The timetable is here. So today we are going to spend a couple of hours together. There is a coffee break at 10:45, and we should end at 1 p.m. You can find the timetable at the events website. There's also information and material to download. So the link will be put now into chat so you can go and grab the material there. And with that, I would like to thank you again for coming to the course, and I hand over to Akhil.
Thank you so much, Karina. It's a pleasure to be here. And welcome, everyone. Good morning. Thank you for joining with us at early hours of the day. I hope we can have some fun while trying to see what real AI systems would look like from an industry perspective while overcoming these challenges together. So let's get started. So let me first introduce ourselves because we just ran directly into the section for files. So my name is Akhil Gopinath, and I work as the Senior AI Liaison at MathWorks. Initially, I was working for the Europe, Middle East, and Africa region, but right now I work as a global AI liaison. And it's a pleasure for me to, be here and share my experience with you. So I have worked with numerous leading industries who are building AI solutions, especially in engineering and science for production level requirements, which includes UAVs, EVs, wireless systems, geophysical systems, chemical industries, and etc. And during those, I would say, collaborative projects, I encountered a lot of common themes when it comes to challenges when people are building their own AI solutions. So today, I'll try to at least share that information with you. So when you go ahead with the process of building your own AI systems or solutions, you have that bigger picture in mind, so that when you have those challenges, you don't need to get started from scratch, but rather have a starting point which you can leverage and build over, right? So we'll be taking a hands-on approach to this. We'll be taking an example which is quite easy for all of us to follow, so that because I'm not sure of the background where all of us are coming from. Some of us may be from a different engineering background or a science background. So I chose an example which is easy for us to follow, but at the same time not trivial, which requires our HPC systems to actually work properly. With that, welcome aboard, everyone. So first questions first. How many of you have heard or have used MATLAB before? Let's say used MATLAB before. Okay. Is there anyone who have used MATLAB before? Octave. Okay, great. Few of us have. Okay. So for those who have used and who have not used, have you heard of MATLAB being used for AI before? Yes, no, maybe, no. Okay, great. Perfect. Okay. So with that, I actually want to go forward with a small thing. Let me just reshare my screen because I don't know if I actually shared it with audio or not. But I want you to see something before we go forward. Okay. So let me, I'll leave you to this. Perfect. So what I wanted to show you are some of the stories where we have been working with different set of people to build solutions. And all those stories that you saw right now are some of the products or workflows that we have supported over time. So we do work in AI, but the only difference is we work in applied AI in many sense where we are translating ideas into solutions. So I hope that gives you an idea of where we are working when it comes to AI. And this is the information I would want to share with you. Great. So before I go forward, any questions? I see there is a question around the slides. Well, the slides are not there in the repository right now, but I can share it with you. So maybe I can share it with Karina and she can share it with everyone. I hope that's fine.
Yes. If you send them to us, we will immediately upload them to the event website.
Perfect. Sounds good.
Thank you.
Great. Any questions regarding anything that you saw or anything that you want to share about what is it that you expect to see from the session? Okay. I don't see any questions in the chat. Okay. Great. So let's move forward then. I hope you will get questions once we get started. So we have seen this video now. So the basic idea is AI is actually changing lives right now, and it's not as difficult when you think about building an AI model, right? Because right now there are so many packages and tools out there, and so many models are freely available as well. But the challenge is, how do you convert this into a real world product? And that's where the real challenge comes into picture. That's where you have to figure out your AI model is no longer just a part of your model ecosystem, but it's a part of a bigger system in itself, right? So I always like to start with something which is very obvious to most of the folks working in AI world, but I still believe that a lot of us actually focus on one key stage in the AI workflow. That is AI modeling, which is all about model development, hardware training, and tuning and etc. But I believe there are important pieces before and after this, which is data preparation, making sure where you're getting the data from, how you're applying your domain expertise to understand the data and make sense of it and make sure it is machine understandable. And once you have your model is rarely something which stands alone. It's mostly in real practical aspect. It works as a small component of a bigger system. And how do you integrate that and make that system work, right? And from there, how do you make sure that the system is working the way that you intend it to? Because it just shouldn't just integrate, it should actually perform the way that you want, right? And finally, how do you make sure that that system can be deployed onto different required architectures? It can be hardware resources like embedded device like your Raspberry Pis or NVIDIA Jetson Nanos, or it can be cloud architectures or ecosystems in your enterprise system. So I hope this gives you a clarity on what AI workflow is and where we are going to focus on, right? So I hope you have noticed this story in one of the parts of the video that I showed. This is very close and very, very impactful story for me. One of the reasons which, motivated me to be a math worker to begin with. So this is a story from Makerere University in Uganda, where there was a lot of infant pneumonia related mortality rate, right? So Brian and his team of students who are working at Makerere University's mechanical engineering department, they wanted to actually build a solution that can leverage their expertise and the doctor's expertise and see if they can bring about a change to this trend, right? And the idea they had was, how is it that pneumonia can be detected? It's basically based on some sensor readings, like how your heartbeat is, how your lung sounds are, etc. Right? So what they thought is, why don't we create a jacket that can connect to a smartphone, which is commonly available in almost every village, uh, and figure out if a kid has tendency of pneumonia or not, and then take them to hospital, which would save their lives, right? So this idea was brilliant, and they actually built it. And UNICEF valued this so much, they actually have placed, I think, initial orders for them. You can check about this on Google search later on. But what I want you to pay your attention on is the story behind how they built it, right? The first and the biggest roadblock they had is understanding their data, because the data of this audio signal that you just heard, it means completely different for somebody who knows who's from medical background and somebody who is not. So I ask you this question: what do you think this audio signal correspond to? Do you think the person whose audio signal this is has pneumonia or something like that? Can you tell me if you can say for sure? Yes, no, maybe. No, of course not, right? Unless you are from a medical background, it's a guesswork. And when it comes to critical systems like healthcare, guesswork is not the best thing to do, right? So you need to bring in expertise of doctors to actually build this. And what they utilized was a tool called Signal Labeler, where they interactively worked with the doctors to highlight and label areas of signals and then figure out, okay, these are the reasons why this audio looks like a pneumonia, possibility audio or non-pneumonia possibility audio, and so on, right? Now, going forward, once you have your labeled data, that's where you can start thinking about how to train your model. But before that, you need to function on your data, right? So you might have to pre-process your data. In this case, it was a signal pre-processing. So if you are an expert in programming and coding, you can go with programmatic approach, or you can use tools like interactive, applications to do this standard pre-processing of data in a quick fashion. And this goes on for getting your features, and then finally you train your train your model. It can be machine learning, it can be deep learning. In this case, they had a machine learning model which they built and prototyped very quickly using this application, which was called Classification Learner app. And finally, when you have your models, you are also thinking about, okay, now the data set is so high or so big and so convoluted. How do I speed up my training process? How do I get to the point where I can actually utilize the resources I have? Maybe I have GPUs on my side, or maybe I have, cloud computing facilities. So how do I leverage all of those? So these are some of the bottlenecks that people need to worry about when they actually are working about AI modeling systems, right? So in short, they built a jacket which can access the data. From that data, they analyze the data with the doctors to label it and then extract features using standard signal processing workflows, then develop a model and then deploy the model as a jacket connected to the smartphone via Bluetooth, based on which the parents can decide whether to take the kid to a hospital to meet the doctor immediately or not, right? Now, why did I say all of this and share this story with you? I want you to focus on the different aspects and importance of each stage when it comes to AI, right? And in industry, all of these are very, very important, especially the first and the second part, because getting quality data is a big, big nightmare, right? So usually when we work in machine learning or deep learning, or let's say, language model development, we often encounter with very clean, very well maintained data set when we are testing it out or when we are getting started. But the reality is you have so much noise, so much, incomplete data that you have to work with, that you have to find tools that will save time for you and figure out how to do that, right? Great. So just to share some of the tools with you, I'm not going to talk about tools today. I'm going to talk about how to get to leverage few of the things, but just for your reference, I'm leaving these uh, possible tools for your work. So these are for transforming image datas and these are for transforming signal datas. Okay, great. Now I have a task for you. I'll play 3 audios and you have to tell me which of the air compressors, these green units that you see on the screen, are air compressors. Okay. And they are the heart of many industries, manufacturing industries, because air pressure, these pressurized air is used for pneumatic controllers, which basically controls most of the things out there in the industry, including safety valves and etc. Right? So having faulty compressor is not exactly a safe way to get going. So you have to be very, very thorough and safe with how do you get to this. So tell me, after listening to this, do you find any compressor which you feel is faulty? So I don't know if this plays now. Yeah, it does. I'm not able to hear anything. Are you able to hear something? I'm not sure if you're able to hear anything. Neither am I, which is very weird because this audio is something that I captured, so I know it plays. But the whole lot of idea that I actually wanted to tell you is when you hear these 3 sounds, you will notice that these sounds almost sound similar. But to a person who has actually heard or worked with compressors for a long time, knows by a few clicking sound that you will hear on the B. I don't know if you will get to hear that when I share the slides. Uh, but when you hear the sound B, you will notice that there is a small clicking noise, which is very faint, but that actually tells you that there is a fault that is there in compressor B. So the idea that I wanted to actually put forward with this example is that we need to have different members of the teams coming together with different expertise to actually build systems which are valuable, right? With this, I also want to share one last thing before we actually get our hands dirty and get going in solving and getting some solutions out there, which is AI modeling is a big I would say needle in a haystack problem, because you have different types of models that you can work with, ranging from machine learning, deep learning, language models, generative AI models, maybe GANs or autoencoders. I don't know, many of those regressions, object detection, semantic segmentation. So there are many types of model paradigm that you can actually select. But the challenge with this is which one is the most suitable for you, right? And usually what people do is they take out examples or they go out and read research articles to figure out what are the general area of family of models they work with. Now, sometimes what you need to do is you need to have some models which are already trained by some of your peers. Maybe it's a very popular model, let's say YOLO models for object detection. You can access those in the MATLAB Deep Learning Model Hub. And if you want to import models from, let's say, other platforms like TensorFlow, PyTorch, Onyx, you can actually bring those into MATLAB, or from MATLAB, send them back to the other platforms as required. You have some examples if you're working in a particular application area, like, for example, medical imaging. You can always find examples that will help you to get started. And if you want to build your own network, there are two ways. You can interactively build using an interactive app, a graphical user interface, where you can drag and drop different layers to build deep neural networks. Or you can select, just drop down menu options for machine learning. Or you can programmatically make advanced deep neural networks by writing your codes. You can have automatic differentiation to build your own custom training loops and so on. So these are examples of what tools can help you with this. And then, of course, scaling up, as I mentioned, we will take a look at those. Now, why did I say all of this to you? Because I personally believe that sharing this as a set of slides, it's like I'm just giving you some information with no clarity of how to actually get going with this, right? That's why I just wanted to give you an idea of things that are available to you, and then focus on how to get things done, right? And also this gives you time to set up everything at your end. So I hope you have all gotten access to one of these at your side. Is there anyone who has not gotten access to any of this till now? Can you give me a yes or no? All of us have access to this now? Okay. Please do not worry about this. Since this is recorded and we are going to showcase all the workflows, you can also replicate this at your convenient time later on if needed be. But be present here so that we can have continuous conversations and see what is going on. Okay. Great. Awesome. So let me go to the MATLAB window that we have out here. Great. So since many of you mentioned that you have not used MATLAB before, just to give you a quick, I would say, sneak peek into what MATLAB looks like, or a quick review. So when you open MATLAB, you basically encounter this integrated development environment, which is very similar to what you would notice also on MATLAB Online. So this is a command window, and this is a workspace where you can see all the variables that will be loaded, and these are the directory files that you would be working with. Okay. Just like any other familiar IDE, maybe like a VS Code, you will have similar tabs and panes. And there are two artifacts that I would want to share with you where we will be working. One is a script, which is a regular script where you would write your codes, and then you will run the file and make it work. And then there is live script, which is an interactive environment where you can run your code and interactively see and interact with your responses and outputs and etc. in the same scripting environment. Just like if you're familiar with Jupyter Lab notebooks, you can say it's an advanced version of Jupyter Lab notebook. Okay, great. So you have access to this folder, right, everyone? All of you have access to this folder? Okay, perfect. So when you get into this folder, I want you to open part 1, which says part1 underscore data prep dot MLX. So MLX corresponds to live script, and when it is .m, it corresponds to a normal script. It's a added information, nothing I would say nothing serious that you need to be aware of, just for your reference why there is MLX and .m and etc. Okay, great. So let me tell you a story that we are trying to do or get to. Okay, so this was a company who actually was working with us. They said that they want to build a vision model or a perception network which is able to do a semantic segmentation, which is pixel by pixel classification in a glorified way of video images when their drones are flying in a city environment. Okay, and the challenge was they didn't have enough information or data set to actually build that model up. So what we thought is there a way for us to use simulated data to actually train the model and then try to see how accurately it works with our real world data, which was limited, but which somewhat available, right? And that's the story that we are going to replicate here. So for those who are interested and excited to know how we got this data, which you will see in the folder under simulated driving dataset, you will see there are multiple images out here that we got by doing simulation. And to get to understand where that simulation goes, you can click on this. Okay, maybe because it is here, but I can probably share this link with you. So you can open this up at your side, or I can show you this one. So what you see is another ecosystem within MATLAB, which is called Simulink, which is a platform for simulating dynamic systems. And this platform, you don't actually code, you basically create a flow diagram of your logic. Okay, so you have different blocks which is available in your library, and then you try to connect these blocks in a logical sense to make your system. And this is the most popular solution for something called model-based design, which is the heart and soul of many industries out there. For example, any car that you use today has model-based design and Simulink underneath it, which makes it work at the moment, right? So what this does is this would do or run your simulated virtual environment, which is set up in Unreal Engine, and then you capture that images and labels in terms of segmentation automatically and save it to your file. So this is how it looks like. This is for drones. I think the one that I had was for with a car. The only difference is for a drone, it is up in the sky, and for the car, it's on the road. But you can create scenarios with varying environmental conditions like fog, snowfall, and etc. based on what are the scenarios you're working with. Okay, great. Now that you have an idea of where to find this, I'll share this link with you. It's the same link, but I think it is. Let me send it in the chat just for your reference for later on. I'll also share this in the final presentation where I send it across to you. Okay. Now, first thing first, what I want you to understand is there are different ways of working with data in MATLAB. Okay. So typically, what is your most favorite way of importing data into a language? Anyone? What tools do you use to import your data? And in this case, specifically, it's an image data set. So let's say, what do you use to import image data? Okay, MATLAB uses a seeing image data store, which is great. But in general, what do you use? If you do not use MATLAB, what do you do? Okay, PyTorch data loader. Okay, great. So for those who are not working with image data, please do not worry. Whatever information that I'm sharing here, this workflow remains the same for whatever data type that you're working with. The only difference is the way that you set up your data and training, uh, and you will notice that it's a minimal change when it comes to how you do that. Okay. The most important thing that I want you to take away from here is the generic flow of information that you will see. And last but not the least, the possible ways of increasing or scaling up your training performance using your HPC clusters or GPUs out there. Okay. And that is going to be the most important pieces for you. And apart from that, I'll also show you a few advanced techniques if we have time, which are hyperparameter tuning, and we also have let's say model pruning, model quantization, and projection. And then last but not the least, how many of you actually are working in deploying your models on some embedded hardware like Jetson Nano, or let's say Raspberry Pi, etc.? Is there anyone who is doing that? Okay, Jetson Nano and Orin. Awesome. Maybe you are putting that into cloud or container services, something like that, or building an application out of it. I don't know. But yeah, if time permits, I can also show you how to, once you have your model trained and set up, how do you get the CUDA version of that code so that you can actually speed it up and also put it onto your, let's say, if you're working on another GPU environment where you need to accelerate it to the best possible fashion using the GPU libraries. Yes. Okay. Okay. Got it. Perfect. And for those who are working in text, just as a forward, uh, if you are interested in, let's say, large language models or agentic AI workflows, please let me know at the end. I will set up some time for you so that we can actually focus on that, because you can actually create your agentic AI flows in MATLAB and also fine tune your large language models or small language models, or in fact, large models, multimodal models, or etc., depending on what's your use case. And if you need API access to, let's say, one of your providers, or run things locally like Olama and connect it to MATLAB, you can do all of that as well. But that's a different piece, I would say. So if you are interested in knowing that, at the end, I can share about it. Okay, great. Now, so first thing first is, from here, I need to actually access all these images which are there in this folder, subfolder. And usually what happens is this is currently very neatly put as one folder for you, but typically the data source for images and etc. is too diverse. There are multiple subfolders or multiple locations, especially when working with an industry. You have different, storage buckets where you can actually have these images or data stored, and you have to have a unified way of bringing them all together. So that way that we have in MATLAB is called data store. Okay. And we have data store for all different types of data set. Like image data store is for images. And you have multiple others like spreadsheet, audio, video, and etc. And you can also create your custom data store. And in MATLAB, if you have ever had any questions or any doubts about something, and you're not sure of, okay, how do I get to this? How do I find a solution for this? All you need to do is right click. Like, for example, if you don't know what image data store is, you can right click and say help. and it opens up the documentation page for you and gives you entire documentation with examples of how to implement it and what are the different things. Okay. And if you want more examples or videos, you can always go to examples, or you can have videos and you can actually check what is happening. So data stores doesn't have a video on its own, but most of the things would have. Awesome. So considering that these are data store, what I also want you to see is what are the other data stores that we have. Let me go to the documentation, and you have, okay, so these are for, let's say, working with large data. I'll just leave you with this for the moment. You can also use Parquet files or something like that if you need it be, but data stores is what we are working with. So you can have all these different types of data stores. And also, apart from this, there are specialized data stores for specialized data set. Like, for example, for audio, we have similar data store, but it is called audio data store with a lot more functionalities dedicated to audio systems, right? Audio type data sets. And you can always have your own custom data stores as well. So here, what we are going to do is part one. I want you to open up a new live script by clicking on either the new live script button, or you can click on the plus button out here. And I want you to try out how to get or create a data store for simulated, simulation driving data set images. So can you try this at your end and tell me if you were able to get a sense of what this is? Because we'll be using this quite a lot now. So I want you to get a flavor of how you code in MATLAB using this. Is there anyone working on MATLAB online right now on this? Okay. In MATLAB online, I'll also give you another task. So you would notice in MATLAB online, you have something called Copilot chat enabled for you. So when you click on that, it will actually give you access to MATLAB Copilot. So MATLAB Copilot is basically an integrated Copilot for coding purposes in MATLAB. It has been trained exclusively on MATLAB documentation, so it gives you more accurate MATLAB code than a regular general purpose Copilot would, right? So this can also actually be used in a very interesting way. You can say that create a image data store for accessing images in simulation driving dataset folder. And it would actually give you a code. Oh, right. I'm sorry. I'm working on the pre-release version. So pre-release version, I cannot share this Copilot code right now, but I can always do it on the other one. So you have this same 25B, which is there in your MATLAB online. You can do this. You have access to if you have a campus-wide license agreement with your campus, you have access to all this already. So you can see it automatically brings in the folders and etc. for you. Of course, it does not know if your folder is having a subfolder or not, because it does not have the context of this right now. For data privacy and safety purposes, we have disabled it. But you can always put that in, and if needed be, you can enable exploring and having awareness to your directory, right? But you get the sense, right? You can run this very easily and you will actually get the information out here. Great. Okay. So once you have done this, I hope you're comfortable with your data set. So there are two data set for you. One is simulated data set, which is under simulation driving data set, where you have images and labels. So just to show you what it looks like, I will load this out here. And then there is cam video images and cam video labels, which are basically real images and real labels associated to those images. Okay. And the way that we created those labels is through apps. You have many multiple different graphical user interface apps that I spoke about. And out of those, there is something specifically for image, which is called image labeler, which I do not see here. maybe the image labeler is not installed out here. But anyways, I can show it to you in my MATLAB. So basic idea is you have image labeler out here. It will come under image processing in computer vision. So you have image labeler. It opens up like this. You say individual projects. It will open up a window for you, which is called image labeler. And I'm going to import a file for the moment, not all the files, just one file. Let me open up some lighter images. And let's say you do not have labeled data for the moment. You only have images, right? How do you label this? There are multiple ways to do this. One is you can add a label by saying what kind of label do you have? Do you have a label for the entire scene? Maybe you have image and you want to classify the entire scene into something, or you have to create bounding boxes or rotated bounding boxes, points, depends on what you want, right? For this case, because we are doing semantic segmentation, I need a pixel uh, based labeling. So what I can do is I can actually say label name is vehicle, right? And I can say, okay, great. So it will create something for me. Now, there are multiple ways to do this. One is you manually go and create your polygon and, select the areas which are important. This is definitely not a vehicle. So this is one. Or what you can do is, let me just erase this. Or what you can do is you can utilize state-of-the-art, I would say, models for automatically segmenting the image. For example, segment anything model. So what it does is it allows me to load segment anything to SAM2 model, and then I can easily segment it. I have not installed SAM2 model because it was big one for me, but when you see this, you will see that I only need to install this SAM2 support package so that I can actually run the SAM model. I can quickly show you how it looks like. You will be navigated to this because these models take up a lot of space, right, on your disk. So we don't ship it as it is while you're installing MATLAB. So you can install the models that you need. Like, for example, if you click on install out here, it will install it for you and you can actually run it at your end. I'll let it happen at the back end. Meanwhile, I'll go back to our MATLAB session on Carolina. Okay. So here what I'm doing is I'm loading my images in the simulation driving data set under the subfolder images. I'm using full file because sometimes you might be working on Linux, sometimes you might be working on Windows. So full file helps you to make the separator based on your OS very, very easy to be put. So you don't need to manually change your separators based on what system you're working in. Okay. And real data set is being loaded from the cam video images. And I'm creating a preview. I'm taking one of these images and then plotting that so that we can have a visualization of it. Just to run this section for you so that you can actually take a look at this. Now, what is happening is very important for you to understand. When I create an image data store, I'm not loading all my data onto the memory. Okay. So data store basically is creating, let me open this one up for you, sim data. It's creating kind of like, as you would be familiar with in C, C++, it's kind of like a pointer, which has information of all the files that it needs to look at, right? And what it will do is whenever you want these files, it will load the necessary files in chunks and to make sure your memory is not overloaded, and then make sure you're able to go through this entire batch of files in a sequential manner. And this also makes sure that if you have additional folders or areas where you're getting files from, you can actually add those in the alternate file system routes, and it will be able to actually point to all of those. And most importantly, this allows you to provide some pre-processing to your data during the time of loading so that you don't need to actually have all the process or the intermediary, let's say, information saved in your memory which would take a lot of memory space for you, right? So this has been optimized for that performance. So once you get that, you will notice that there are 5 classes that I'm going to work with in this image. I have classes for roads, background, pavement, sky, and car. Okay. And when the original dataset was created, it had these additional classes, which was building, trees, traffic lights, and lights. In order for us to save some time and also some memory to improve our efficiency, I'm clubbing all of this 4 categories as a background category. Okay. And these values were given to me by the person who actually made the labels for this particular data set. Okay. And it needs to be accurately mapping those values. And once you have these values, what you can do is then you can run this. I did not run my previous section because I just skipped it. So I can run this section, or you can run this in 2 ways. One is you can go to a section and say run section, or you can run the entire script by saying run all sections. Okay. So I'm running it also by a shortcut, which is the blue bar on the left side. I have this, and then I can run this. And what I can notice is this is how the images would look like. On the left side is a segmented image of my simulated environment. On the right side is the segmented image of my real image that I had. Okay. And now what I'm doing is after this, I'm just partitioning my data into 20% for 80% data set, 80% for training, and 20% for validation. Okay. And I'm using an inbuilt function for doing this because it's much convenient for me to do this in this way. And I'm going to leave you at this point right now. Okay. Have you followed me until this point? Is this clear to you? Can you give me a yes or no? Okay. It's clear. Great. Any questions related to your domain here? This is for people who are not working with images or working with a different type of images and etc. Any questions you got from this section yet? Yes, no. Okay. What would be the advantage of using MATLAB over standard? Okay. Very good question. And why don't we take this question at the end of this session? And if you can give me an answer to that, that means I have been able to share something which is valuable. If not, then we can have a discussion more, right? To figure out what is the advantage that might be valuable for you, because it depends also on what kind of use you have with the machine learning system as you would be working on, right? Sounds fair? Does that sound fair to you? Awesome. Great. Perfect. Okay. I will take a quick jab at part 2 as well, since you have run this and you have seen what is happening. So part 2 is actually about training your model. Okay. And I will leave you for 2 minutes to read through this file and have an understanding of what's happening. Okay. So take 2 minutes, go through the file, part 2A, actually, the part A of part 2. Just go through this file and get an understanding of what's happening. You don't need to understand the syntax. Just understand what's the flow. What are we trying to do here? Okay. Now let's see. So this section is completely on model development. Okay. So we already have all the data by running the first part in our workspace. As I said before, workspace is a very, very valuable object at MATLAB, in MATLAB. You have different types of visual I would say visibility on the variables that you are working with, so it makes it very easy for debugging. And it also gives you functionality to figure out different information and properties about your data. One of the most important ones I always enable is bytes, which gives me an approximate idea of how much memory is being consumed by my data set right now. For example, this is the data size right now, but this is small because it needs to be divided by 10 to the power 1024 squared, right? Great. So now going forward, so what we are doing out here is we are creating something called Deep Lab 3 Plus network, which is based on the backbone of ResNet 18. This is a pre-trained model, okay, architecture, which is very popular for semantic segmentation. Now, before this, why did I choose this, or where did I get this from? I want to show you an app that we spoke about before. What if you want to build your own neural network from scratch, but you do not want to write complex programming codes for that, right? That's where this application called Deep Network Designer that you will find in your apps section come into picture. So let me try to see where the window went. Okay. I'm trying to make sure everything that I show is running on Carolina, so you have the same experience while working here. So when you open your Deep Network Designer, it opens up a start page, which gives you multiple different options, okay? It gives you an option to build your network, blank network. It should be having some icons. I don't know where they are, but you can import your network from Workspace. You can import your network from PyTorch. For that, you need to install a small support package, but it's very easy. You just click install, and it's similar to what we did for our segment anything model. Or you can import your network from TensorFlow. Both of these directly you can import in a graphical user interface way using Deep Network Designer. And there are some pre-trained network that you can work with. This is pre-installed for everyone's QuizNet, but for other networks, figure out which is it that you want to work with, and you can actually install those network. Okay, and you can use it. And you have variety of those. For example, here we don't have ResNet 18 that we want to work with. So what we will do is we are going to install this. I want you to actually do this process. Oh, right, we are on Carolina right now. So the add-ons process would be a little different. Let's see if I can actually get this from here. Okay. If you have the browser open at your side, you can say ResNet 18 MATLAB. And you will see deep learning toolbox for ResNet 18. I'm sharing this in the chat. Perfect. You can just download this and keep this in your Carolina ecosystem. You can just run this in your Carolina ecosystem by uploading this in here. I will leave you to do that part, but just making sure that we get this properly. I can do this in an easy way, which is I can put it for you all in the file section, so you don't need to worry about this. I will do this in this section itself. I can upload it here, right? So you should all have access to this. I'll do the same for all the packages that I'm actually using. I can share the link with you and you can do that on later stage. Okay. Did I upload that? Okay. So those who are working in Carolina, you should be able to see now that if you go to your CD, if you use this function, which one is not recommended? Are you referring to this? Okay, let me go to files. In the same folder, you would notice you will have this ResNet 18 MLPKG install. You can double click on that and it will open up your MATLAB add-on manager. Oh, this one is because when you used to have ResNet 18, It was a DAG network, which was directed acyclic graph, right? So what happened is we used to have different architecture for different type of neural network before. And it was very confusing because you have to have different workflows for different types of neural networks. So what we did is we combined all of those into single architecture, which is image pre-trained network. And from there, you can actually now bring in all these networks. So now what happens is whenever you have a neural network, deep neural network in MATLAB, you will actually get a DL network object instead of a DAG network. And DL network object automatically resolves everything, whether a DAG network, series network, whatever type of network you have, it automatically takes care of it. So you have a unified workflow, which makes it all easy. Hope that helps. Folder permission denied. Yes, you will need to actually copy it in your side and get it working. I am not particularly certain what's happening on this end for me, because when I try to do this, okay, let me show you the steps as you would do it. Create a copy of this in your work file, or maybe before that, just for the sake of it. Okay. Not sure, but this display is not coming. It seems to be something with the display of OOD for the moment. But no worries. Let me show you the workflow so that at least we have some direction of looking at how to do this, right? Meanwhile, and also it's about time that we actually take a break. Oh, you don't have permission to go to that. That's weird. Okay, let me take a break and get back to you with a simpler example, or simpler, let's say, process, so that you can actually able to get this done. Or you can, this is not ideal because we need a unit architecture, which is ResNet 18. Otherwise we do the heavy lifting. We do it through our import workflows. But anyways, let me share a workflow with you. In 15 minutes, we'll take a 15 minutes break. I'll get back to you with the workflow, and then we can get started from there. So you can also have some coffee, because I definitely need some. And we'll be back in 15. Okay. Does that sound okay to everyone? Meanwhile, I'll share the steps of what you can do to get these models in MATLAB. Okay. Perfect. Have a good coffee break. Just a quick check. Are you all back? Can you give me a reaction or something? Coffee rate. Awesome. Perfect. Great. Okay. First thing first, I wanted to show you the deep network designer. So I'm going to do that first. So Deep Network Designer is a graphical user interface where you can interactively build your network or import your network from different platforms. Okay. Now, what I want to show you is how does this look like? So for example, if you want to build your network, the way you would do is, let's say you want to build an image classification network or something. So you can drag and drop your layers depending on what kind of image you're working with. Obviously, let me actually make it wrong. And then you can have n number of different types of layers out here. And the best part is you can also have custom layers if needed be. Okay, but not here. Obviously, you can have it outside, but you can have custom function layers out here. So that is called function layer, which you can search. The function layer, where you can actually have some functions written for you. Okay. So the idea is you create all these layers and networks, and or if you already have a big network that you need to visualize, this gives you a very easy and interactive ecosystem to do that. And what you do is, if you click on any layer, you will notice that the properties of the layer come in the right side, and you can quickly change the properties, like what kind of normalization you want to work with, or what kind of dimensional normalization you want to do. Like, for example, you want to do an element-wise normalization, or channel-wise, or global normalizations, right? And so on. So you have that for almost all the layers that you can have access to, and you can get all of this going on. Okay. Now, what's more important is once you have built your network, you can analyze the network to make sure everything is connected properly and there are no errors. For example, here, because I wrongly used convolution, one-dimensional convolution, it says it's not meant for two-dimensional images that I have already selected out here, right? So I need to fix it by changing it to a two-dimensional convolutional layer. And when I do the analysis again, I can then just do the analysis, and you'll notice the error goes away. And it gives a very good overview of the number of parameters, learnables that are there, and what kind of layers there are, and etc. with a tree structure for my network. More importantly, there is something called analyze for compression. Okay, so when you do that, it ideally analyzes what kind of layers do you have, what kind of network do you have, and gives you an estimate of what is the possible compression you can do. So if you have the current network, which is 3.5 kilobytes, if you do pruning, you will have 3.5 kilobytes. There is no much pruning that can be done. By projection, you can actually have a 91.3% possibility of reducing this. You can reduce the size by 91.3%, not possibility, right? And by quantization, you can reduce it to by 72%. So this is the idea that it is giving you with regards to how you can reduce the size of your network or compress it. So later on, you can choose what method you want to work with. Okay. And last but not the least, you can export your network as an object in your workspace, or you can create MATLAB code that can be utilized, that can be then utilized for you when you want to, build over your MATLAB code. For example, this is the MATLAB code for devising or building this network, right? And then you have another functionality, which is you can export this to Simulink. Remember Simulink? It's the platform where you can simulate dynamical systems. So you can actually export this into Simulink. So just showing you how it looks like. So it shows me in a more interactive way how exactly the Simulink system would look like. This is very, very practically useful if you're building systems. For example, you're building a UAV-based systems, or if you're building an electric vehicle, or you're working on satellite imagery where your data is coming from some remote, location, and then you have to access it and etc. So this is how the model looks like. So you have image input coming in from here, data flows from here, it does the necessary layer transformations here, and then it gets you the output. So this is for a simple network that we created. But if you want to open a network from the workspace, the network that I have already created, right? So I can say replace that network, this network, with the one that we have in the workspace. So this is how ResNet 18 based, Deep Lab would look like. So you can zoom in and you can take a look at all the different layers and etc. and how things are, right? And of course, you can always, move around and make things a little bit more beautiful if needed be, or you can say auto arrange. Awesome. Quick questions, if there are anything on this. Any questions? Any questions, any doubts, any comments? So while you are thinking about the questions, I can share one insight. So whenever I work with teams who are dealing with extremely large networks, or who want to integrate different networks for, let's say, advanced workflows, they find this visual representation quite powerful and saves a lot of time for them, especially when they're importing networks from different platforms, because you still have the same flexibility of Deep Network Designer as you would have for internal models. So I don't see any questions in the chat. Okay, great. So moving forward then. So you have this network. Then you're setting up your training options. These are basically defining what kind of solver you're going to work with. I'm going to work with adaptive momentum solvers. What is the parameters, hyperparameters for trainer, or the solver, I would say. So the initial learning rate scheduling, you can do all of this. If you are not sure of what the training options would be like, as I said, right click, say help, and learn more. you will be taken to the web page where you will be able to read about all of these different parameters and what they do and etc. in detail. It gives you everything in detail. Okay. And if you want to do any kind of advanced analytics, like let's say what algorithms are being used, it will also tell you about the algorithms that are being used out here. Okay. Great. Now going forward, one option that I have not put here, but I have put here is execution environment. Okay. And this is one of the most important things that I believe is very valuable. Once you have built all your network training loops and everything, right? What if I want to accelerate my training process on a GPU, right? So you can always just go and set this flag, which is called options.execution environment, and you can flip it to the environment that you have. For example, if you have just a CPU, obviously you have to use a CPU, but if you have a GPU, you can use a GPU. If you have, let's say, access to multiple GPUs at your side, you can actually have multi-GPU support. If you have, let's say, if you have a larger multi-core GPU that can actually have parallel computing going on over the GPUs as well, you can have parallel GPU support as well, right? Now, the best part is this works on your cluster as well. So if you're doing this on Carolina on the on-premise way, like we did, right, with Open on Demand, if you're on there graphically, you can actually do the identical workflow there to make sure you're using the nodes that you have access to in that particular session, right? So all you are doing is changing a flag and you can access the environment automatically. So that's one very, very powerful difference that I often, find when working with MATLAB, especially on the deep learning part of things. And then if you notice, almost every inference function that you have, for example, this is specifically for semantic segmentation, so as to make it easy for you to get your predictions out. Because semantic segmentation, your actual labels, when you take a look at labels, you would notice this is also an image. This is also an image. So these are huge data set, right? And when you have those huge data set, it might quickly eat up your memory and put you out of memory. So what these functions do is they have been specifically created for your use case. So when you use semantic segmentation for getting the scores from your network and then converting that to labels, it will automatically, instead of saving it in your memory, it will save it in your disk, right? Under the folder test results. And then what happens is only when you need this information, you can retrieve that from your disk rather than having to save that on your volatile memory, right? And then you get your metrics accordingly. So just running this, you can see that how it runs. And you will notice that it has a different approach to it. Now, I have a quick question to all of you. Why do you think I have used mini batch size as 4? Why didn't I use, let's say, 10 or 16 or 20 or something like that? Any ideas? Perfect. Yes, exactly. So my GPU, just to show you how it looks like once it is done. So once it is done, I can actually show you something, and then it will give you an understanding of why this question is extremely important. Yeah, it's evaluating metrics, and I actually asked verbose to be off, so I don't know how many images are done, but it takes around 2 minutes because we have 701 huge images that needs to be processed. And even with the GPU, it actually takes its own sweet time. So meanwhile, any other questions till now? While this is running, it will take a few more minutes, but yeah. Any questions till now? Okay. Great. Coming back to the question, right? Why mini batch size is important. So let me show you my GPU device. Okay. So as I mentioned before, I have a 5060 Ti. It has around 17 gigs of memory. out of which 15 is available for me, right? Now, the catch is here. When I actually use GPU computing, it's basically my data is going through the available memory on my GPU, right? So if my data set, if I take a simple look at my image, there should be a real image here, right? It's a huge image, if I'm not mistaken. It's a big image that we have, right? And when you have image plus label, which is also of same size, not this one, it's in this is around, yeah. So it's also a big size, right? It just doesn't have three channels. It has just a height and width. It's a single dimensional matrix. So when you combine this and you have multiple images loaded simultaneously, it would actually eat up your memory. And there is a possibility that if you use too big a batch size, you will not be able to, get things moving on. It would have a memory leak issue. And if you have too little, then you will not be utilizing your, GPU enough, because you do need to understand that there is always a communication overhead that happens when you're working with GPUs, because everything that goes and computes in the GPUs, it will then be gathered together to make sense for you in your CPU, right? So if you underutilize it, it will waste time. If you overutilize it, of course, it will not work out for you, right? So mini batch sizes are very important, and I always suggest have an understanding of your GPU or computer architecture and make sure you are able to use an optimum number of mini batch size. And there is also a systematic way of figuring out what is the best mini batch for you. I can share that with you in the fourth stage, okay, or next stage. Great. Now, what I have shown you is a process and a method in which your system is on the premise. Let's say if you're working on Carolina, you will open up MATLAB, you will follow the same flow for running it on Carolina if you're working with open on demand. Okay. So the part B, as you would notice, of this section is actually talking to you about how you can set up your cluster to work remotely. So that means if you have your MATLAB on your system, let's say your laptop, your desktop, you can actually set up your cluster, whichever cluster you have, and you can actually make it work. You can submit job remotely and you should be good to go. So that means your system would be free, your job would be running on the cluster, and you would be getting your results once the job is done or if there is any feedback, right? So how do you do that is the question. So in MATLAB, setting up your cluster is actually relatively simpler in many sense, because this is if you are, let's say, if you are on Carolina, but you want to submit a job and get off of Carolina and come back later on, then fetch the job and make sure everything is there as your results are there. You just don't want to use the resources actively all the time. This is case one. Case two is you want to use your MATLAB desktop, but you want to submit your job on your HPC cluster or your cloud computing cluster, and you want to submit the job and get the results once they are done, right? These are two scenarios. So for either of these scenarios, the first thing is for you to set up your cluster. And how to do that? So in MATLAB, you would notice there is this environment tab under your home tab. So when you go into the parallel part of that tab, you would see there are multiple options out here. Like you can select your parallel environment. You can select your GPU environments if you have multiple GPUs. And then you can also create and manage clusters or discover clusters. So if you are, let's say, in the same network as your HPC clusters, you can always discover your clusters. Or if you're working on, let's say, AWS or Azure, there is something called MathWorks Cloud Center, which allows you to automatically set up your cloud there easily, and then you can use on MathWorks Cloud Center to explore your possible clusters. Okay. So this is one way of discovering your clusters automatically if it is visible. Most of the time, when you're working with HPCs, that is not the case. So what you need to do is you need to create and manage your cluster. Okay. And for Carolina, you will have a similar process for it. Let me show you that. So when you have MATLAB out here, yeah, MATLAB. Okay, it's opening up this one. Nonetheless, so I can share it with you later on, I guess, because I'm not exactly familiar with this website yet. But just to give you an idea, you will have a document or a downloadable file which would be provided by your system administrators. Okay, and what it will contain is this information. So when you go to cluster profile and you say you have a HPC server, you will not be doing this when you are having those downloadable system. But what you will need is configuration, right? You will configure your cluster, the folder where the data would be shared, number of workers available for you, the computational threads, root folder, head node, cluster version, and then what kind of licensing are you using? Because you will need a license to run MATLAB, right? So you can use the license that you have, which is always online license. So you can say true. So you can easily log in with your MathWorks credentials and all that. So what we have done is, instead of you having to manually do all of this, we have a configuration file that we have worked with our, your system administrators actually. So if you reach out to them, they should be able to give you this configuration file. All you have to do is run that configuration file and it will automatically add a cluster in your name. So that would say, then you will have a parallel computing environment and it will have something like this. So I have this cluster profile. So you will have a cluster profile for, let's say, Carolina. You will have it for Carolina. If it's for any other HPC clusters you are working with, you will have that for here. So then what you need to do is you just need to switch your cluster profile to that if you want to do that in default, but I would recommend not to do that. Then what you need to do is, let's follow up on our workflow. Let me just close everything. Okay. So in part B, what you need to do after that is, once you have your cluster set up, okay, you will be able to get the name of your cluster in the pair clusters menu. Okay, so you have to create an access point to your cluster. Right now, I'm creating a cluster for my system, PC, okay, because I do not have access to the HPC cluster right now. So I'm going to use this. So you would have name of your cluster out here, like HPC something, 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 whatever name you give. But for the moment, it was processes. So I'm just leaving it at that. Now, what you have to do is, how do you send job to your cluster, right? So we are going to make sure that the options that we had set up here, remember the options that we had set up for our training, these options, we are going to utilize what is the best environment for us. For example, I want to use GPU, not multi GPU, maybe because I only have access to a single GPU on my cluster. Okay, so what I do is I select that, then I, instead of using train net, I actually use batch, send this information to my cluster, run this entire script, which is called model def. This is the script, right? Run this entire script on my cluster, use these many workers, and make sure you capture all the outputs that the that is being generated by this script in your diary. This is the meaning of this this section. Okay, and this tick and talk is basically for me to understand how much time does it take for my job to get submitted. Now, what happens at the back end when this is going on, right? When you do this, when you're running the script, it automatically figures out all the variables in your workspace. When you run this script, whatever variables you get on the workspace, it is automatically transferred to your cluster. So you don't need to manually do that. But it is always recommended that the data set that you work with is there on your cluster, and the file system is pointing to the data set which is there on your cluster. Because what happens is otherwise you will be unnecessarily uploading your data set from your MATLAB to your cluster and then doing the job again and again, which will take a lot of time, right? So that is how you do it. And by doing this is just, you're good to go. That's it. You don't need to do anything else. So if you notice, I'm just trying to send this job to my system so that we can take a look at what is happening. It should ideally give me an error by now if my system is busy, but it is not, right? So what it has done is it has scheduled a job to be done. So how do I look at that? I can go to parallel. There is this something called monitor jobs. Okay. So when I monitor job, you will see this job is currently being running. But this will not be going forward because my parallel process pool is not open. Okay. So in order for this job to be done, I will say start parallel pool. And now the job will actually start running on my cluster. And I can always take a look at what is happening by refreshing. Okay. So you can see how many storage bytes is taking and what is happening and etc. I think I ran it twice and that's the reason it was not coming up before. So now what you can see is since the job is running at the backside, I am free to use my MATLAB the way I would usually use it, right? So like magic. So this is very, very useful, especially when you have extremely wrong jobs that is running and you don't want to, freeze your system while the job is running from other jobs. You can actually submit your job, let it happen there, and then, just focus on the things that you need to work on. So I can check my job state, which is running. And if there is anything, it will show me all the outputs that is being generated by the script here. So for example, dairy is capturing, this was the first output that was created, of course, which is the first output that is created in my original script, right? And go on. And you can wait for the job to get completed if you want to actually wait for the outputs first. And then once the job is done, you can say, fetch outputs, give me the results of what you found, right? So I'm going to let it run at the back end because, of course, we have enough time to do this. And when you do this, especially with your clusters, it becomes extremely, extremely valuable. Because what happens is you are now scaling up your entire process onto the extended compute capacities which is there on your HPC cluster. So you don't need to worry about GPUs or CPUs, etc. It's all in the cluster, and we have taken care of this slurm and everything at the back end for you. So you don't need to do any of those. All you need to do is submit your job like this, and it's good to go, right? Now, quick check. Did this make sense? Did you understand what I was saying till now? Or is there any questions, queries, or something which was not clear? Yeah, T4 GPUs are actually pretty old, and I'm pretty sure that we are updating those. I think we have Tesla's are compute capacity 7 or something, right? So they are old, and I think almost all the HPC centers were running on Teslas are also updating those. So we will also be doing that. We have not done that yet because most of us have really nice AWS accounts provided by the company. So we use that when we have to do large scale compute. Let me just show you how the cloud center looks like just for. Oh, yes. So that means when you say training has stopped because criteria met, that would mean that one of the stopping criterias have met. In this case, I had put a stopping criteria that if the validation accuracy is not, or validation loss is not going down for 4 iterations, that means you have trained enough, just stop it. It's my own logic. It does not have any logical backend on that. It's just for us to not do overtraining, just for demonstration purposes. But in real life, you would have to figure out when should the training stop. What is the criteria for it? Okay. Okay, so it's called cloudcenter.mathworks.com. This is how it looks like, just for everyone's awareness. In case if you have ever worked, or if you need to work with cloud compute, which is also a possibility in future. Great. Now sticking to our HPC resources. Any questions till now? Now coming back, so I said there is a systematic and smart way of tuning what kind of hyperparameters you need to work with, is like mini batch sizes for solvers, or even for your network. Figuring out how many filters do you need, what's the right set of depth of your network, and etc. There is a systematic way of doing that in MATLAB. We created something called Experiment Manager, which you can find out in your applications out here. It's called Experiment Manager. Okay. Now, what does this Experiment Manager do? So let me just open up an experiment that I created for you. So it allows us to create or design experiments that you need to do on any kind of workflow. So right now I'm using this for our deep learning model hyperparameter tuning, but you can do that for any kind of experiment design that you might have. Okay. Especially for people who are, let's say, working on something like where they have to compare between parameter tuning and tweaking, and have a logical understanding and sweep of those parameters by leveraging the information that the model is going to give them. This is a very, very useful product for those. So how does this work, right? So in this, you can actually set up all the different hyperparameters or things that you want to search or tune, right? For example, in this case, let's say I wanted to tune my initial learning rate. I can add that. Or if I want to tune my mini batch size, so I can say mini batch size, right? And I can define what values I want to do. If it is exhaustive sweep, that means it will go through the individual values that we are giving for each of the hyperparameter. Like for example, it will go for one experiment with initial learning rate as 0.1 and mini batch size as 0.32, and then go on with all the combination of possible hyperparameters out there, right? This might not be what you need. You might want something which is more finer, something more like an optimization, right? So you can always go here and you can say Bayesian optimization. So when you select Bayesian optimization, then you have to provide range and type of the function, type of hyperparameter that you're trying to tune. So it should be from minimum to maximum. So you have, you can actually go in that direction. So Bayesian optimization would actually take an initial guess and then go into the domain and try to find optimum for you. Attempting to find, of course, a global optima, but it's not always certain, right? You have to do iterations. And if you have some amount of transformations that you need to do, for example, if you have a string-based or categorical array, there is always a coding that you need to do so that your optimizer is able to figure out what is the numerical equivalent of it, right? Now, once that is done, what you can do is you can set up your experiment. What is it that your experiment manager is going to run to search or tune these hyperparameters with? So just editing this. This is something I've already set up for you, and you will notice that it is very similar to what we have seen. So this is in case if you are, so this is just for housekeeping, so that I am in the right folder when where the data set is. Otherwise, typically what happens is your data set is in this folder itself. And you don't need to do this. This is just housekeeping, nothing as a workflow. Okay. It's the same process that you would have seen. I'm loading my data as image data store, setting it up with labels, partitioning it, training data, validation data, right? And then setting up the image size and network, defining my network, defining my loss function, which is exactly the same loss function that you would have seen. I just put it up in a different file just for the easiness of it. And then you have options, right? The training options. What Experiment Manager does is it takes all this information, because I created a train net experiment. Okay. So it takes all this information and goes back and puts it into TrainNet and runs the training over and over again for all the different parameters that you have set up. For example, the parameters I initially had, right? It was for my initial learning rate. So that was solver parameter tuning. So I can actually have this come in just like any other optimization would do, right? And when you do this, this experiment keeps running and running and running, and then you are able to, get to a solution. And you can also have custom metrics to look at what is the output that you're getting. For example, here, your custom metric is looking at global accuracy. Okay, exactly the same thing as I did before. Loading real data, real labels, and then predicting it. If I run this, let me actually show you how it looks like. I can go and run this. Now, before I run this, I want to show you something more. If I want to scale this on my cluster, right, you have multiple options. You can select simultaneous or sequential, but batch. You can do a batch simultaneous one. You can select the cluster that you want to work with. For example, if you had HPC cluster somewhere here, you can actually select that HPC cluster. And then you can select the pool size and then just run. And it will run in the cluster for you. For me right now, I don't have any clusters except for what I have, right? So I'm going to run this in sequential manner just because I don't have multiple GPUs. And when I run this, it will set up the experiment for me with all the information that I have given and run the experiment one by one. Okay. And I can annotate, filter, figure out what's happening, etc., by easily going through the process. So right now it has going through the first iteration, which is the hyperparameter for learning rate is 0.1. So I'll let this run at the backend so that we can take a look at the results. Okay. So I'll pause here for questions. Any questions? Is this something useful for you? And as I said, this is not limited to deep learning. You can have experiments for almost any kind of activity that you do, even simulation. So you might as well create simulated data for foggy environment, rainy environment, all this environment by using Experiment Manager. Great. Any questions, anything that was not clear, anything you want me to, repeat or clarify? And best part is, I'm not sure if you're aware of this, but I hope you are. But a lot of people do ask me one thing. They have their workflow already in, let's say, Python or PyTorch, etc. And can they use Experiment Manager to fine tune their workflow in Python? And the answer is yes, you can do that. By leveraging this, using MATLAB with Python or Python with MATLAB, whichever is, it can go vice versa, right? So if you're running MATLAB on Python, you can use MATLAB engine in Python. Or if you're calling Python libraries in MATLAB, you can do that directly. So when you do that by using a simple suffix, which is py, after setting up your environment, you can actually do the same experimental setup and get going. So in your experimental setup, you will be, instead of invoking the functions which are there in MATLAB, you can invoke the functions in Python, and you can leverage the Experiment Manager to tune all the parameters. Okay. So we take a 5-minute break after a little bit more time, right? Okay. Awesome. Great. Now, this is stage 1, right, of what we actually saw. So the experiments are running at the back end. So you can see the experiments are running. And if you want to visualize the training plot, you can actually see the training plot. And it will keep going on. So, but for the moment, I'm going to stop this. I'm going to stop the training. So what it is going to do is it's going to stop the experiment for me. And then it will try to run the metrics, which I don't want it to run. So I'm going to close that as well, because I want to quickly make sure we are able to go there. You see, it's running the metrics for inference. So I'm going to close that. I'm going to interrupt all of that because I want to actually come back and show you something else. You can run this, keep it running at your side. So that's completely fine. Okay. Now, what is it I wanted to show you? Okay. You have all the things that is technically there for model development till now. You have the data preparation and modification, managing large amount of data and etc. You have seen how you can build your neural network or manage your neural network, based on different tools and also in programmatic aspect. And you also have seen how you can easily scale up on different compute resources that you have access to both locally and remotely, based on just switching a flag, or submit your job remotely as a batch operation so that your system is free to work with. And last but not the least, you also saw how to set up experiments so you can tune your hyperparameters or run your experiments in a sequential manner. Now, all of this is good, right? All of this talks about data management and model development and etc. But more importantly, where does this all fit in, right? So usually what happens is all of this model is just one part of your process. The second part of the process is, where is this model living, right? Where is this model lying down? And why is that important? So let me quickly share a story with you so that we can truly appreciate what is happening on that front. Okay. I hope you're able to see my screen. You are able to see my screen, right? Okay. So this is a company called Avilis who actually created an autonomous drone. The task of this drone is to first search for stranded skiers or mountaineers up on the snowy mountains and rescue them when needed. Like, for example, if there is an avalanche or something like that, right? Now, the challenge in this is, when you build systems like this, these are safety critical systems, right? And you need to make sure that whatever tools that you are actually building is able to work in a very, very close, tight-knit manner with the actual real system, right? That is the drone itself. And because lives are dependent on it, and also the hardware is pretty expensive, so you don't want to break it. So there is always a question: how do you test your AI so that it can crash, but at the same time you can predict when your AI will crash, right? So there are many things that is necessary for us to do that. Remember how I created the simulated environment data? This was using Simulink, right? So in similar manner, what you can do is you can always create scenarios to make sure that your data set for first stage is complete and comprehensive of all the edge scenarios or unforeseen conditions that can be there, right? That's step one. Second is, when you have your model, which needs to navigate in an environment like this, you need to make sure that this model is actually working properly, right? It's able to control, for example, this drone. When your navigation model is saying there is, let's say, an obstacle that needs to be avoided, it will give the direction to the drone to move left or right or go up or down or turn and etc., right? But what if your model takes 2 seconds to actually make this decision and then send it to your model? What will happen? Is that something that you would want? Let's say you have a smart car, autonomous driving car. It takes 2 seconds for your model to actually make a decision. Would you want to travel in that car with that auto automatic driver assistance system. How many of you will like to travel in a car with that? I'm pretty sure none of us would, right? So the idea is, with regards to systems, it is very important to understand where our AI model is going to live and how is it going to interact. The example I'm showing is a simpler one because it's something that we have all seen. Cars and drones are something very common nowadays. So this is a typical lane following algorithm system or lane following system, which is a part of automobiles, right? And what you can see is there is a small portion which says vision detector, and everything else around it is very, very critical. The dynamics of how the vehicle will move, how the lanes would be followed, how the multiple sensor information is being fused together, and etc. Right, to make the decision. And when this all happens, you have to make sure this all happens in the required time frame and time limitation, right? So just to show you how this looks like. So if your system is bad in terms of timings and in terms of decision making, by the time the lanes are changed, your car will actually hit the other car, right? So it's not feasible. So these kind of ecosystems allow you to integrate your AI model into a wider system to test it properly. This goes beyond just a system. It can be a small component also. For example, if you have a battery management system, which is a part of your electric vehicle, right? Uh, and you have an AI system which is actually figuring out how much charge is there in the battery. Your AI system should actually be relevant and good enough to actually depict the real battery. Otherwise, it's going to be a mess. It can catch fire, it can explode, and so on, right? And last but not the least, after building these systems as robustly as you can, uh, almost all the industry folks would say no to your model being integrated into their systems if it cannot be verified and validated for performance, right? If it cannot be explained why that particular model is behaving the way it is. For that, you need some formal ways of verification and validation. So for AI verification, one of the most important validation that needs to be done is robustness. You don't need an AI model which would take an image or a system input with a slight noise. It will start, going all about wrong in the wrong places, right? For example, if this was a AI model which is made for, let's say, a drone flying in a mountainous region, a slight noise can make it feel like it is going to hit a mountain and crash, which is not the case, right? So how do you formally make sure your networks are robust and make sure the authorities who are going to incorporate this are able to know about this, right? That's where formal verification and guarantees become important, and you need tools to do that, in a more robust manner. For example, this is a verification library, part of verification library, which is called formal verification for robustness, where you can actually add different set of noises to your data set and try to see if your model is able to overcome these challenges or not. And at the same time, it can also act as a way for you to train your network with noises, so that when your network is trained, it already is incorporating all the possible disturbances that is going to be there in real world, right? Second thing is making sure your network follows physical constraints. It should not be that when you have a model, AI model developed, uh, when the battery is being charged, it should not discharge, right? It should logically charge. So physics should be conserved. So for that, you need to have some constraints in place when you're training your systems and when you're functioning your systems, especially when it is applied to real world systems like UAVs or EVs or even your medical devices. Because a lot of devices like pacemakers and etc., they have batteries in them. And if you are estimating it in the wrong way, it's a very, very dangerous situation. So you need to have constraints when you're training your deep neural network. So that's the second set of verification that you can do while you're building your system. And then, of course, there are formal ways of figuring it out during simulation and testing. For example, if it was an automatic or pilot, autopilot that you have on your aircraft, if all you have built is your AI model, which is capable of working in a very clear weather, but then suddenly there is a dust storm and it does not know what to do, what do you prefer? What should your autopilot do if it is seeing a dust storm and it does not know what to do? What would you prefer your autopilot does in that scenario? Can you tell me? You have an airplane, there is an autopilot that you built AI model for, but suddenly there is dust storm which you never trained it for. What do you want your model to do? What would you prefer that your model does? Any guesses? Would you want it to still attempt to do what it decided is the best probability? Okay, I like this answer. It says, tell me it doesn't know. Exactly. Anyone else believes this is the direction to go, or should it just go with what's the most probable category of decision it has decided based on computation? Okay, give me probabilities, then let me decide. Perfect. So you agree that there needs to be the model needs to be handing over the decision making to a human being, right? That's precisely what simulation helps us do in these scenarios, right? So you have to build systems which, in case if your outputs are not strong enough, right? If the distribution is not exactly in the same parameters as it has been trained for, it should rely rely that information to the human being or the controller and say, this is out of distribution, you need to make a call, right? And it needs to be tested for almost all the scenarios that is possible and conceivable for a particular system. And that's why you need scenario level simulations and testing. So this is one example of how we did it for the drone company, which you saw before. Now, going forward, in industries, there needs to be certifications, and these certifications are something which are more standard in nature. Like, for example, autonomous systems or aerospace systems have DAL certifications that need to be done. So you need to have tools which can actually put those guidelines into practice when you're working. And these are some of those workflows that help you to do this. Okay. Now, I'm going to pause here because I wanted to give you an important idea towards verification and validation, right? Before we actually take a break. And I want you to think, is this the only thing that is necessary to make sure my system is safe to work with? Is this the only things that is necessary to make sure that my AI system can be successfully deployed in the real world? If not, what are the things? Think about it, and then we can circle back after, let's say, 10 minutes, 15 minutes. Any thoughts about what are the other things, or if there are any other things that you need to consider before your system is ready to uh, be deployed in the real world? Yes, no, maybe. Anyone? Great. So the question was, is there anything left that we need to consider before we can use the AI system that we have built in the real world? Anything you feel we are missing? Validation. Uh, Validation with what? Speed, memory, accuracy. What do I need this speed, memory, and accuracy for? I mean, I can put this on a GPU, right? A big GPU, and try to make it as fast as possible. What is missing? Yeah, that's a good guess. Okay, I'll give you a hint, everyone. Where is this all located in real world? Right now it's in our computers, but in real world, where is all this located? All the things that you're building, all the models that you're building, or all the codes that you're writing, where does it live? Right, chip. So let's go a little broader in that. So what is a chip? Embedded systems, yes, it's hardware, right? So ultimately what happens is one of the key things which is important that we still need to actually work on is how all of this will behave when living on the same environment that it needs to live on in the real world. For example, if my automatic driving system is to function in real world on a car, my entire system should behave the way it should on a car, right? It should not be other way around. So we still have to figure out how to do that, how to how to bring our system, the models that we have built, into the real system. And that's a very important step when it comes to certifying our AI for safety critical applications, especially. And that's where model based design is very important, because when you build components and systems, you continuously, during each stage of your development, you validate, verify, and make sure that your system is actually meeting the actual physical requirements. So you start with building your components, you do a software in loop testing where you have the entire system in software world, and you're integrating your different modules and making sure everything works. Then you make the decision go into your processor, which might be a different device, right? And then you connect it to the rest of the simulation that you have in your system. So that's a processor in loop simulation. Then you have hardware in loop simulation, where your plant is on the hardware and you're trying to make sure everything communicates and behaves the way it does. And once all of this is done, then you finally actually can say that your system is verified and validated to work the way that you intend to in the real world, right? And this entire process is what takes industries a lot of time, and it is highly documented and highly structured process. And what is the key component that you feel is necessary to make this work? What do you think is one key component that is necessary to make this work? Yeah, hardware, absolutely. Hardware is definitely important. So sensors, cameras, the microprocessors, the processors, everything is important. But in order for all of this to work, what is one thing that is there? So if you have to make your model run, let's say you have a model and you want to run that on an NVIDIA Jetson Nano, right? What do you need? Compute power, absolutely, you get that from the hardware. But what do you need to get your systems onto the hardware? Okay, good try, but it's not data. Okay, that's a good direction. Have it in CUDA or driver. What does that mean? What does that mean? Very good direction, Tom. Container, absolutely. Exactly. Generate code. What code? What code are we referring to? So if, let's say, if I did not know English, right? Let's say I knew, uh, I knew, let's say, Spanish, for example, right? And you wanted to tell me to do something. What would you do? You know English, I know only Spanish. So what would you try to do? Exactly. So basically, what you need to do is you need to translate the codes that you have written into the language that the hardware can understand, right? Or the system. It can be anything. It does not need to be only hardware. As Tom rightly mentioned, it can be a system of, in a software environment as well, or an enterprise system. But considering the most of the physical systems are hardware based, let's stick to hardware for the moment for ease of understanding. And doing that translation is the biggest pain point that you can imagine. Because when you do translation, there are many things that can go wrong, right? Sometimes when you translate something, it might sound awkward in the language that you translate it to, because it does not follow the same phonetics of that language, maybe when it is the verbal language. In similar fashion, when you're translating code from one platform to the hardware platform, there is a possibility that your translation is not behaving in the same way as it was when you were using one of the tools, let's say Python or MATLAB or anything else, right? So that is a pain point. Any other pain points you can imagine? Take a guess. Any other pain points you can imagine? When you translate your code so that you can integrate it with different systems, what other challenges you can think can happen? Any guesses? You've guessed wonderfully before. So please feel free to do that. Compatibility. Absolutely. Whether the thing that you're translating into is compatible with the hardware that you're actually working on. Missing library, loss of efficiency, brilliant. No, actually, there is no one API that connect all things like this in the practical world right now, because all these hardwares have different, let's say, ways they interact, right? So, for example, if you are working with, let's say, Jetson Nanos, they have their own way of the understanding the deep learning models, right? They have CUDA CUDA toolkit to understand the architecture of how the network would look like, and cuDNN artifacts to make sure that it is optimized for that particular graphical processing unit, and so on. So the point is, all these languages have different things and requirements, and hardwares have different requirements. So it is very, very difficult and critical at the same time to actually make sure that you are getting the right stuff onto your systems. And that's where one of the most important things that we at MathWorks work on come into picture, which is automatic code generation. So what does that mean? That means whatever your system may be, whether in MATLAB Simulink, whatever system logic that you have built, AI or non-AI, you can develop codes for different hardware from the same ecosystem without having to rebuild your model. You can automatically generate production level code, which is following all the coding parameters and paradigms that is necessary for any industry. And you can use that to generate CPU codes, GPU codes, FPGAs, containers if needed be. You can generate C++ code for generic, integration later on, and so on. So you can do all of that. And this eliminates the possibility of having human error when it comes to translating from one platform to another. And this is the most important piece that is offered or used by industries when it comes to MathWorks, right? Now, how do I do this with my deep learning model that I have built is the first question that would come, right? So let me show you how it is done. So as I said, everything in MathWorks ecosystem have two ways. One is the way of applications, so that it is easy for anybody who is not a MATLAB expert to get to things. And the other one is through programmatic approach, right? So what I'm going to show you is the graphical user interface approach. Programmatic approach is something which we can extend further. So for translating between one platform or one language to another language, the product family line that is always there in MATLAB is called coder. Okay. So you have coders for HDL, GPU, MATLAB, embedded devices, etc. So for our means and purposes, what we need is a GPU coder. Okay. Because what we have is a GPU system, right? So I'm going to say GPU coder. And I'm going to just start with this one. So I'll say semantic segmentation coder project. Okay. It will create a project for me in the folder that I am working out of. And it will give me all the options necessary for me to generate, in this case, if it is, this is GPU, so it would be CUDA code or CUDA library if I need one, right? So what I need to do is, if you notice out here, I have an option, right? I can choose what language I need to get to. If it is CUDA, I'm going to select CUDA because this is GPU coder. What is the output that I need? I can get output as a library. a static library or a dynamic library, an executable if I want to, just run that, or if I want MEX. MEX is MATLAB executable. That means when you MEX something, it goes in the base language, which is C, C++, right? And that means MATLAB will execute this in a much more faster. The inference will become much faster. So for this purpose, let me actually create MEX, because it can then, or rather, let me actually create a dynamic library, because I think that's most commonly used when you integrate it, right? There are two things which is necessary when you actually try to generate code for anything that you are looking at. First is creating an entry point. That means there should be a function which should be able to invoke and give you the model that that needs to be executed. In our case, I've created this function called segnet predictor. It's a function which will take input and it will load a network. The only difference is I'm saying the network is persistent variable, that's all. If the network is not existing, you are just going to load the network by saying coder.load deep learning network, and I saved the network after training as trained net.mat. Very easy to do. You just say save and save the network variable. That's all. That's how easy it is to do in MATLAB. Okay. So you load the network and then you say input is a deep learning array which has the following input format, SSCB. I think this, you're familiar with this format, right? Paradigm, SSCB and etc. I hope you are. If not, you can let me know. I can probably drop you a documentation link to this. And then you are running the predict function, which is not, which is going to predict using this network, using this input, what is going to be the output scores. Okay. Okay, SSCB is basically telling what dimension correspond to what type of metric. SS is, the way I kind of read this is, SS is space vector, because I work a lot in physics, so I actually consider this as space. So SSCB is space or x height and width in terms of images. C is the number of channels and B is the batch number. So if you have a matrix or a vector, let me show you something. If I have this, right? Let me run this entire section. It's part A, data prep, just to show you how the data would look like. Okay. So in my data set, if you look at my image has 3 dimensions, right? Height, width, and number of channels. So that is S, S, C. And then I will have multiple images that will be fed to the network at the same time, right? So that would be batch. So B is the batch number of images that I would be feeding together. That is B, the batch parameter. Does that make sense? Does that clear? If there is anybody who has more elegant explanation to this, please feel free to share that. But this is just my personal way of understanding what this is. It's basically to make sure that when you take a model or when you share this model with someone, you will have to say that my model expects my input to be in this format. The first dimension is going to be height, the second dimension is going to be width, then third is going to be channel, and the fourth is going to be the batch size, and etc. And this is different for different platforms. PyTorch will have a different one. The TensorFlow will have a different one, and etc. etc. So I hope this helps. Great. So now I can add this entry point function. I just need to click on entry point, and I can just type the name of the function, which is which was what? It was segnet underscore predictor. Okay. And it should automatically pick up that function for me. Oh, what happened? Did I break it? Okay, let's see. I'm in the right folder. It's there. Oh, okay. I think it was my parallel computing turned off. That's created an error. Anyways, so once you have inputted your entry point function, it asks you what is the dimension and type of the input that you're expecting from here. Okay. So you can define that as a different kind of input based on your own understanding if you already know the signature. If not, what you can do is you can say using command window, I'm going to, or using a script, I'm going to give you an example of how to call this function. Okay. So I'm going to use a command window for this. And I'm going to do this, start this, and I'm going to start recording this. So I have my image already, which is sim image. So I'm going to say predict using network. Oh, sorry. I have to use this function, right? Segnet. So I'm going to say segnet predictor. And I'm going to send it the input, which is a sim image, simulated image. And this image should be of single data type because it's deep learning. And I'll get the output as scores. Okay. So this is what I will do. So when I run this, it should ideally give me a response of scores, which is what I'm getting out here, right? Scores for 5 classes or 5 categories that I have. And now I can stop this. And what it does is it automatically figures out what is the input being given, what is the dimension for this, and etc. So I can actually say what this is. I can say this is a GPU array or it's a sparse array. What is it? So if it is a GPU array, this will be accelerated and run on a GPU for compute. Okay. So I'm going to say this is a GPU array. And I can say this is unbounded or bounded depending on what is the network that you have set up. If your network expects a very stringent, let's say, image input, then you have to bound it. If it does not, you can unbound it, or you can unbound it lower or unbound it open, depending on what it is that you want to do. Okay. Now, once this is done, you're all set. All you need to do is generate code. And what it does is it is now automatically generating code. And it will take a bit of time to translate it. And you will see there is a invalid problem because I actually accidentally missed the dimension, add a dimension. This is 3. I did not add that dimension. You notice I removed that dimension accidentally. It was 720 1280 cross 3. So if I generate the code now, it should actually work because it needs a 3-channeled image, right? So it's generating code, and you can see the code will always be coming up in the right side. I'll show you once it is done. But while this is happening, it should not take more than 1.5 minutes. Any questions till now? Anything that is not clear? Anything you want me to explain again? Okay. So what you can see is the code has been generated, and this is the report of the code generation. So what you can do is you can trace the code. So these are the code files that has been created. This is the translated code, the CUDA code, as you can see, and also the header files and etc. And you can trace this in your code. For example, where is my prediction happening? So you can see this is where the prediction has been defined, right? And you can exactly mark and trace where your code is actually functioning. Where is DL array coming in, or where is your data loader coming into picture? So all of this can be traced very easily to your file, which has been generated. And you can also go for your build logs if there is anything, and you can check the variables, whatever variables there are. Okay. And you can package this in whatever way you want, depending on what is the requirement for your system. And then you can export this as well. So What you have gotten is an entire library. Just to share this with you, you see there is this code gen that you also have downloaded. You will see there is a dynamic library file that has been created for you to integrate this the way that you want it to with your system. It also gives the report in an HTML format and gives you an example of how to invoke this function or this package when you want to work with this. So this is code generation for you in MATLAB for GPU code gen. Now this code gen can also happen for your hardware. For example, if you want to deploy this on some some NVIDIA Jetson Nano or something, you can actually select your hardware. After going to settings, you can select which hardware you want to work. So you have option for NVIDIA Jetson Nano, Raspberry Pi, ROS or ROS2 if you're working in robotics, or AMD tool chains. If you have anything, you can do that, and many other tool chains that you can work with, that you can actually use to make these generated code, right? So these are some of the things I wanted to share with you with regards to hardware deployment or in general deployment. And when you change the language, you can obviously go to any other language as well. And some of the people always ask me, can I translate this into Python if there is any functionality which is out there? So yes, you can do that by using Python package compiler. You can package this into Python if needed be, or .NET, C, C++, whichever you need. It's all for you, right? Awesome. So any question? Is this clear to everyone? Yes, no, maybe. Okay, on a scale of 1 to 10, how important do you think this is for you? 10 being very important. Yes. Yeah, the process remains the same for different architectures. Process remains identical. So you do this for one. If you want to change anything, you go back to your coder, change the settings, do it for any other architecture, you can go with it. And if you have any, let's say, custom boards, a lot of people do work and build custom boards and etc. You can actually invoke your own tool chain, bring your own tool chain into MATLAB or Simulink, and then generate codes for that particular custom hardware as well. That's a bit involved process because that requires you to basically tell MATLAB how to translate it. But once you set it up for the first time, then you can do that without any setup required for the later durations. I hope that answers your question, or did I misunderstand your question? I don't see anything. Oh, best practice. Yes. The best practice is always, I would say, self-served in many cases. It depends on what is it that you want to do. I always say best practice to, as some of the things I would do always when porting is making sure I have a way to measure the equivalence of my platform, have some sort of test set up for the code that was originally there and the code that is ported to a different platform. For example, if I was doing a hardware code generation, I would first create a MEX. I would first create a MEX and create that test that MEX in MATLAB to see if the outputs are adequately or not adequately. It should be identical. But obviously, based on what is the compiler that you're using, there might be some floating point challenges. But beyond that, it should be good. It should be, similar. And then you can be sure that, okay, your DLLs are going to perform in a similar fashion. And after that, again, we come back to our presentation stage where I say, when you have it in code, you also have to check whether it is going to behave the same way in the hardware or in the processor that you're working with. Because the processors also have different, I would say, compute packages at the back end. So depending on that, your accuracies and your floating point errors can accumulate, and then you can get a different result. So what is the drift that you have? You have to quantify that. So that's my only 2 cents, I would say, in that context. which is very critical in space applications if you have even 8th or 10th decimal place difference. So depends on what's your use case. I hope that that gives a bit of an understanding. Awesome. Going forward. So another thing to consider when you're working on hardware is memory. And somebody did rightly mention this. So you don't always have a GPU that can run a very heavy model. Let's say a large language model is not going to survive on a microprocessor with few megabytes of memory, right? It needs to be some sort of hardware that actually can support it. In similar fashion, there are some applications, for example, for lane detection and etc. It is something that requires to be on edge device. So it needs to be small and it should be computationally efficient enough to work in the constrained environment that there is on those embedded devices, right? So if that is the case, you need to have a very robust way to figure out how to minimize the memory footprint and make sure that you are able to get your network to be as small as possible without losing on the accuracy. There are many ways to do that. One is obviously where you pick your model based on understanding in the beginning part itself that this model is something that needs to lie on a specific hardware. But once you have that, and let's say your model is still big, then you may have to simplify your model architecture. You have to figure out how to use the most relevant parts of your model and maybe simplify the rest of the part which is not as relevant or as contributing. Or you have to quantize the accuracy of your model, maybe the floating point accuracy of your model. So maybe instead of working with 8-bit data, you might want to work with 4-bit or a half bit or 2-bit, depending on what kind of system or accuracies that you are comfortable with. And at the same time, it is very, very important to understand what kind of floating point numbers are run on the hardware that you're working with. Because I have always encountered people who might have done a 4-bit quantization, whereas the hardware requires an 8-bit computation. And what happens is it try to dequantize it to 8-bit and then run it, making the system very, very slow. So you also need to be aware of that. So putting it forward, what does this actually look like when you want to work with this, right? So pruning is one of the ways where we try to reduce or remove the least important pieces of your model architecture. And the way that we do it is through a process where we fine tune the network, figure out what weights are important and remove the least important weight, and then evaluate after retraining whether we are having good accuracy or acceptable accuracy or not. Ultimately, with the acceptable level of accuracy, you should get a network which is much smaller than your original network, with only weights which are important captured and the rest of redundant weights or less important weights removed. This is one way. Another way is projection, which is not something that I've discussed here, but you can actually go back and take a look at that in the same directory that I shared in the link. Second is quantization. So for quantization, what you need to do is similar to the application that I shared before. In MATLAB, there is a deep network quantizer application that you can find here, deep network quantizer. And the best part is it will walk you through how to do this. Like step 1, you get your network loaded, right? Step 2, the networks are represented in a different way. It's basically we are trying to figuring out what is the most significant bit in that particular network. And then we go by summing out all the different layers and the significant bits and try to see which is the most important bit out there. And then we try to prune it according to that from a set number of size that we are trying to explore. And then based on that, we evaluate our network and we try to figure out how to quantize that by rounding it off by certain logic which is set, right? So you can check this out. And the best part is all of this, when I show you this, all of this has an option for you to scale it up on different platforms. So when you calibrate, you have option of calibrating it on a GPU, and you can again export this as a code, and you can put this as a batch on your any of your clusters out there, right? Now, I know there is too many things that has been covered today, but I wanted to give you a practical exposure to the kind of nuances that people face when they are building these systems in real world. And I also wanted to have enough time left for us to have a discussion on other type of techniques and tools that you might be interested in, right? So some of the key takeaways that I want you to keep at the back of your mind: AI is not just modeling. There is an entire system that needs to be considered. And it is important to understand what platform to use, when to use, why to use. I'm not saying you should use MATLAB alone. Well, that's what my job asks you to. But in reality, I believe that every tool has its own importance. And there are tools which are good at something, and there are tools which are good at something else. As an interfacing tool, as an integrating platform and a deployment platform, I think it's very, very good if you can test out MATLAB and Simulink and figure out what kind of functionalities is suitable for your requirements. In real world, explainability, robustness, testing, validation, verification is very important, especially if you're trying to make a product out of this work that you're doing. Even if it does not involve hardware, if it's still software, it still requires to go through a lot of compliance requirements that needs proper systematic evaluation. And it does not need to be difficult. If you want to deploy your AI models into different platforms or different architectures, you can do that quite well. So these success stories that you saw in the first video, or many more you will see later on, they are all happening right now. So it's not something which is not possible, or it's a hope. It's something which is currently happening, and you can also get it going and doing. There are a few resources I've linked here for your reference if you want to take a quick overview of how to do a certain activity with MATLAB if you're new to MATLAB. If you are not new to MATLAB and if you want to dig deeper into some of the techniques out there, you can also have some focused learning paths. So once you get the presentation, you should be able to see all of these links and access these. And last but not the least, you can always reach out to me, connect with me. I'll be happy to work with you at any point of time. And it's a pleasure to be talking here. And with this, I will probably stop the stuff that I wanted to present right now and focus on the Q&A and also talking about LLMs and generative AI. So I think I'll just shift my gears a little bit and probably show you that and then open for questions. Does that make sense?
Yes, Akhil, thank you very much for the lectures and everything. And for sure, we can go through the questions in the chat. If somebody has a question, just feel free to unmute yourselves, I suppose. And we will also put into chat the satisfaction survey, which we will obviously share with Akhil after the course. So please, before you leave or start to do something else, don't forget to fill that for us as well. It's very important for our continuous improvement. And now, please go ahead and place your questions if you have any.
Sure. Just before the questions, I just wanted to share something on generative AI and text analytics, because a lot of people were mentioning that. So in MATLAB, as I said, you can have different generative models that you can build. But for text, I would say most important thing is there is something called LLMs with MATLAB that gives you an interface of connecting different different language models directly into MATLAB. You can do that with local host like Olama, or you can do that with OpenAI or Azure OpenAI services, etc. And there is something called MATLAB MCP core server that lets you to basically connect MATLAB to any of your MCP host, like VS Code, Cloud Desktop, or anything of that sort. And you can actually use that for agentic workflows as well. This is an example video of that. I can share this presentation also when I share the other one with you. And last but not the least, MATLAB Copilot is there, and there is for you, you can also try out Simulink Copilot, which is out there for beta testing right now, and it will help you to integrate the coding capacities of a Copilot within MATLAB, and you can explore how to do this in a more interactive fashion. So Copilots have different use cases, like you can chat or generate code, you can get explanations, create tests, autocomplete, error generation, and so more. So you can actually explore this, effectively. And all of you have open access to the MATLAB online license that I shared with you until the next week. So please feel free to play and use GPUs and etc. as much as you need. And let me know if there are any challenges. I'll always be happy to connect with you. So yeah, so that's a short thing I wanted to share with you. Open for questions now. Any questions, any doubts, anything that you want me to share information about later on? Uh, all yours right now. Okay, I don't see any questions. I hope you found this useful and valuable, and I was able to add some additional information to your knowledge base. If there is anything that you feel I could not cover, or if you feel like you need more information about or something that you are exploring, let me know. And I'll be happy to share with you that information and help you out in any way possible. So as I said, you already have access to tools and everything. And if you need support, there is me, and I have my entire team who will be very happy to help you and support you in any ways that we can practically possible. And have a lovely day. Thank you so much, Karina and Petra, for enabling us to have this session. Since we don't have any more questions, I think I'll call it this a day. Thank you for sticking by me for this long. And if there are any particular topics you want to think about or you want to interact in future or learn about, let Karina and Petra know, and we will actually set up something more focused in your field. Thank you so much for your kind words, everyone.